All right, hello everybody, and it's with great excitement that we welcome you to the 2021 Virtual West Conference. We're very excited to this year have participants not just from UBC, but also from across Canada and across the world. So through West, we aim to create a space for global water conversations. And this is because we understand that the water challenges of our future will not be solved by either technical brilliance or innovative policy alone, but through the combination of these and many other things. So this is the vision we have, is that water challenges must be addressed as necessarily interdisciplinary. So through West, we're aiming to bring together experts of many of these backgrounds to share their research and experiences in the hopes that we can all learn something new and from understanding somebody else's approach. So first, I must thank our West Conference Organizing Committee. West this year has blossomed into a very multidisciplinary event, and that was something that's only possible through the hard work of our organizing committee, who are themselves a very multidisciplinary group from across UBC. So to our team, thank you very much for months of hard work to make West happen. Next, quickly, we'll thank our sponsors, the UBC Alma Mater Society, UBC Applied Sciences, Chemical and Biological Engineering, UBC Future Waters, the UBC Civil Engineering, and the Canadian Association for Water Quality all contributed financially. And thankfully, we're happy to say that because of low overhead costs with hosting a virtual conference, most of these donations translated into prizes for the student presentations. So thank you to our sponsors. While we couldn't host an in-person networking session as part of the conference, our team conceived the Water Industry Showcase, which is happening tonight from 4:30 to 6:30 p.m. In Vancouver Pacific time. So please do check that out. And thanks to our water industry partners who are attending the event, of which there's about 8 of them. Some are NGOs, some are engineering firms, some are municipalities. Next, so at West, we aim to unite researchers from across the globes. So something cool that we did over the last year with the WESTalks seminar series is we were able to make a global map to see where our fellow conference participants are coming from. So in a second, I'll post the Padlet URL link again. And that's, so if you click on that link, I encourage you to, there's a red plus sign in the top right corner. If you click on that, you can type in the city and then click enter, and that'll add a pin on the map to where you're calling from. And with that, we'll be able to build a map of where in the world everybody who's a part of the West Conference is calling from. Finally, while we're looking for collaborative ways of addressing our future water challenges, it's very important to remember that all of our water has been here since forever. And long before we were here, the Indigenous peoples on whose land we live, work, and play were the water stewards. And so I recognize that here at UBC, we're gathered on the traditional, ancestral, and unceded territory of the Musqueam people. We're so very thankful for the countless years of responsible stewardship that has allowed us to enjoy the clean water, the fish that swim in them, and the wonderful weekend adventures that they afford. So to begin our conference, I'm very excited to welcome Elder Jewel Thomas from the Musqueam First Nations to say a few words. Elder Thomas, would you like to take over?
Okay. Good morning, everyone, and welcome to Musqueam Traditional, Ancestral, and Unceded Territory. Water. We need water to live. I'm sure you've heard all this before. However, it bears repeating and highlighting. Not just our water is clean and tastes good, but the water in this country is in jeopardy. We haven't had oolakan fish from the Fraser River for many years. The last few years, we haven't had our sockeye salmon. These fish are vital. They're vital to us, and they're lifebloods to our people. In rural Canada, for many generations, they've been on boil water regulations. We're fortunate in Vancouver that our water is safe and clean. But still, people have to buy bottled water by the case every single day. I think it's Nestle who buys Canadian water, bottles it, and sends it all over the world. It will take many people with dedicated minds to solve these urgent problems. Now I'll say a short prayer for you. God bless this gathering. Help them to open their minds, hearts, and spirits. May they receive comfort and inspiration. Bless your families back home. Very special blessings to the people who have been residential school survivors and the people that are grieving in Kamloops because of finding 215 bodies on the school grounds. Thank you for this day and thank you for our blessings. God bless the children. Amen. I have another short one for you too. Humankind has not woven the web of life. We're but one thread within it. Whatever we do to the web, we do to ourselves. All things are bound together. All things connect. Chief Seattle, 1854. So have a good day. Whatever he's saying, I can't hear.
Thank you very much, Elder Thomas, for your words. That was very, very kind. There's many lessons, I think, that we can learn from thinking differently about our relationships with water, and the Musqueam and the Coast Salish people have a rich history to learn from. So thank you. I will, once again, I mentioned a second ago, I would post the link. So there we go in the chat box. There's a link to the map. And I again encourage you to share with us where you're calling in from as we build the global West Conference map. All right, so with that, I'm going to hand it over to my colleague Fuhar Diksik, who will introduce our first keynote speaker of the conference, Dr. David Sedlak. So thank you all for joining us this morning, and I hope that you enjoy the next 3 days of the West Conference.
Thank you so much, Carl. Good morning, everyone. Welcome to the West Conference. And with great honor, I would like to introduce Dr. Sedlak for today's opening keynote. So Dr. Sedlak received his undergraduate degree from Cornell University and a PhD from the University of Wisconsin at Madison, and then spent 2 years as a postdoctoral researcher at the Swiss Federal Institute for Environmental Science and Technology before he joined the University of California at Berkeley in 1994. Dr. Sedlak's research focuses on the fate of contaminants with long-term goal of developing cost-effective, safe, and sustainable systems to manage water resources. He is particularly interested in the development of local sources of water. His research has addressed water reuse, the practice of using municipal wastewater effluent to sustain aquatic ecosystems and augment drinking water supplies, as well as the treatment and use of urban runoff to contaminated groundwater from contaminated industrial sites as water supplies. In addition to his laboratory and field research, Dr. Sedlak is interested in developing approaches for managing urban water cycle. He pursues these efforts through research coordinated through the National Science Foundation's Engineering Research Center for Reinventing the Nation's Urban Water Infrastructure, also known as Renew It, the Berkeley Water Center, and the National Alliance for Water Innovation, or the NAVI Hub. He's also the author of Water 4.0, a book that examines the water in which we gain insight into current water issues by understanding the history of urban water systems. And in particular, if you haven't read that book, you should give it a read. With that, I would like to invite Dr. Sedlak for today's talk.
Thank you, Fuhar. Let me get my talk up here on the screen, and let's see, get it into full screen mode. Okay. Thanks again, Fuhar, for the invitation to be here. Thank you to Carl for organizing the conference, and thank you to Elder Jewel Thomas for hosting us on her lands and representing her people. I want to spend the time, I want to welcome you to the conference, and I want to start off the conference with maybe a little bit of a bigger picture view of the world by thinking about this question of how we solve the world's water problems. I have a very clear recollection of being a new graduate student and all of the things that I had to manage, figuring out classes and how to conduct research and how to write papers and how to navigate a faculty advisor and even how to live out on my own. And the idea of figuring out the big picture of how my research fit into a larger context was something that was very challenging. And I relied upon my elders, my faculty supervisor, my guidance committee, my professors to help me see these things. And I also spent a lot of time as a graduate student trying to figure them out myself. But really, it's not until you have quite a bit of experience that you gain some of the insights that are really necessary to understand where things are going. So in my case, my students don't really let me come into the lab anymore to do research. So here I am with all this time on my hands to think about the new paradigms facing water systems and the ways in which we might solve the world's water problems. And that's what I'd like to talk to you about today. I'd like to share with you. And maybe as you start your journey as graduate students, or those of you who are finishing up and getting ready to go out into the world, can take this as a little bit of a guidance as you set your own path. So let me start by talking about the things that environmental engineers have done well historically. And that's something that we sometimes refer to as the hard path. So if you think about the history of water resources and environmental engineering, throughout the 20th century, we created an incredible infrastructure of managing and storing and delivering water, especially in the years after the Second World War and the rapid expansion that came to be known as the Great Acceleration. We built an incredible infrastructure of dams and water storage projects. In fact, between 1950 and 2000, the world built about 40,000 large dams and created dozens of large interbasin water transfer projects like the one shown here in Lake Mead in Colorado. These projects dwarfed the aqueducts of the Roman Empire or the quanuts of ancient Persia. In addition to just providing water for cities and industry and hydroelectric plants, this modern water technology allowed us to enable the Green Revolution, which helped alleviate some of the problems of world hunger. So here's a picture of center pivot irrigation systems in Kansas, the United States. But this is a pattern that repeated around the world where we access groundwater to provide water, which was really a big piece, this irrigation that was created of feeding the world during the Great Acceleration. Now, beyond the costs of all of the concrete and the steel that was needed to enable us to access all these water resources, the world paid a steep price for following the hard path. Tens of millions of people were displaced by dams and water projects. We extracted water from aquifers and sucked them dry to the point where land subsided, as shown in this picture from California's San Joaquin Valley, where in a period of about 50 years, the land sunk by about 9 meters. Entire lakes disappeared, as shown in this picture of the Aral Sea disappearing from starting in about the year 2000. And a lot of this was due to the unrestrained development of the hard path approach that we took to enable water. So by the end of the 20th century, the world had started to recognize the true costs of the hard path, and it had lost a lot of its luster. And so during this period when we were coming to terms with the downsides of water development and the hard path, people started to talk about the soft path. And this paper, which came out in Science in the year 2003 from my neighbor Peter Glick, really reflected this changing trend that people had of thinking about global water resources. And this advocacy for the hard path basically said that in our haste to build out the soft path, we had forgotten about ways to make water systems more efficient. And if we took a lead from the field of energy, where things like the compact fluorescent light bulb and more efficient automobiles allowed us to get more out of using less, we could make significant progress in the soft path and not have to build more infrastructure and maybe even liberate some of the water systems that we had so much damage during our rush into the hard path. And we can see evidence of this all around the world. So here's a figure from the Seattle public water utility showing the increase in population of Seattle, especially in the period after World War II. And in the early part of this period, during the time when we were still enamored with the hard path, the amount of water that people were using in Seattle was growing in proportion to the population. But by the turn of the century, there was a decoupling. And that was due to the soft path. That was due to people giving up on lawns. That was due to more efficient indoor plumbing. And this pattern repeated around the world, not just in the municipal sector, but in the power sector. So you can see here in this figure, withdrawals of water for thermoelectric power, probably the largest source of water withdrawals in the world. And you can see in the United States that the amount of water taken out of the environment to cool power plants has started to come down after the turn of the 20th century and continues to come down and is projected to shrink even more as we decarbonize the energy system, but also as we move away from once through cooling to recirculating power. This idea of the soft path and getting away from excessive water consumption has caught on with industry. And we see figures like this coming from various water groups and that are echoed by industry of pursuing the idea of the circular water economy to complement the whole idea of the circular economy. So there's seen as a merit on its own accord for taking water and reusing it over and over again, whether that's in an industrial process, whether that's in a municipal setting, whether that's in agriculture. And so you have the confluence of the hard path projects that we built during the 20th century, and now the soft path, which allows us to get more out of them. And in many parts of the world, water scarcity is a remote concern. Maybe there are people who have lots of water and worry about the safety of the water, but my concerns have been with the people who are running across the issue of water scarcity. And so water scarcity is an issue that we hear about all the time in the news these days. This is a photo from one of the largest reservoirs in California. Actually, it could have been taken last week, but it was actually taken during the 2015 drought. And it comes up over and over again that changes in our weather patterns and our inability to keep up with the water demand of agriculture and cities is leading to water shortages. And when you consider the magnitude of these shortages, they're not the kinds of things that we necessarily are going to be able to solve with our existing hard path infrastructure and the soft path approaches that we've developed in the last 20 or 30 years. Consider, for example, the case of Phoenix, Arizona, shown here, where the metropolitan area is expected to increase by about 70% between now and the year 2050. And the average number of days when the temperature exceeds 38 degrees centigrade is projected to triple from 40 to 132 a year. This hotter climate is going to increase outdoor water demand, just as the amount of water available from the Colorado River coming into Phoenix here, shown in the CAP project, is going to decrease. This source of 40% of the city's water will shrink as there's more contention over Colorado River water. And if you look carefully at the homes shown in this picture, you'll see that there aren't that many lawns, that a lot of the soft path solutions of getting to desert-friendly landscaping had already been taken. And when you look around the rest of the world, you'll see many cities that are struggling with water challenges and the inability of both the hard path and the soft path to meet the challenges, whether it's Mexico City or Perth or Chennai or Cape Town, they all face different kinds of challenges that will not be solved purely with social changes or policy changes. Now, in some cases, these cities are located close to places where there's plenty of water for agriculture, and agriculture typically uses something like 10 times as much water as cities. And so it may be possible to reappropriate some of the water from agriculture, but the farmers are not going to give up on their irrigation water without a fight. After all, in that same period between now and 2050, farmers are going to need to increase their harvest by about 70% to keep up with growing demand of food for a more populous and wealthier world. And all of this is going to happen in the light of climate change. So here we stand in the year 2021. We've seen what the hard path can do, and even though it's had its downsides, it's really the root of our water supplies for the world. And we've seen the wonderful things that the soft path has been able to do for us in terms of making the world's water use more efficient. But really where we stand now, and as we think about our research and our careers and the things that we want to accomplish in the coming decades, we think about what comes next. And that's what I want to talk about today, something that I'll refer to as the next path. This idea that we can't get where we want to go with simply the hard path. We can't get there by complementing the hard path with the soft path. It's time to do something different. And that different thing that we hope to do is an all of the above approach that incorporates the best of the hard path and the best of the soft path with an increasing understanding of our place in the world. And when I think about our place in the world, I think about our obligations to future generations that the world is grappling with as we come to terms with things like greenhouse gas emissions and climate change. In a very similar way, we need to think about not only what our water situation looks like in the next 5 or 10 years, but what it looks like to the generations that will follow us. And so I've been very fortunate over the past year to be distracted from the pandemic and a little bit occupied by this assignment that I was given by NAWI, the National Alliance for Water Innovation, to lead a process that we referred to as road mapping. And this road mapping process that we've done is we've looked at the water needs in the United States in 5 different sectors: power, resource extraction, industry, municipal water, and agriculture. And we've asked the explicit question, what can new technologies, in particular desalination technologies, do to enable more effective use of water in the coming years? And so we've thought not only about desalination and new technologies and how they might help us get through our challenges, but we've also thought about some of the policy and social and economic challenges of bringing those to fruition. And in the time I have today, I want to share with you 3 main observations from the road mapping process. Again, these roadmaps are available online for free. You can see the link on the bottom here, or just simply search NAWI roadmap and you'll find it. But I want to highlight 3 areas, and I think they relate to some of the things that people are presenting at the conference this week, and some things that you may not have already been working on, but where your research may find context in the future. So the first theme that I wanted to tell you about is the information technology revolution. And for the past 2 decades, folks have been telling us that an IT revolution that's disrupting every other sector of the world is finally going to hit the water sector. And certainly the idea of digital water has been intriguing to people for a number of years, but it really hasn't lived up to its full potential. When we look out into the next decade, we see this idea of digital water or digitization of water really starting to make a big difference on how we manage our infrastructure, much in the way in which it's affecting transportation and electricity. And so, this idea that we can have sensors and actuators to control systems when people aren't there, that we can take advantage of massive computing and things like satellites, really has a lot of potential. And I want to just give you a few examples of where I see that having an impact on the water supply challenges that the world faces. So the first one that I think is really going to be very important in the future is to use the improvements in weather forecasting to better operate water storage systems, dams and reservoirs. So over the past 3 decades, satellites and radar systems coupled with global circulation models that are run on supercomputers have increased our ability to predict when it will rain and to know how much water is going to fall. And on the West Coast, we receive a lot of our water through a phenomenon known as atmospheric rivers. And that's these phenomena that bring large amounts of water onto the West Coast and rain in very specific areas in a very short amount of time. About 100 kilometers north of San Francisco, in a place called Sonoma County, the Water Agency has partnered with researchers from the University of California's Scripps Institute of Oceanography to predict the paths of atmospheric rivers. And with that, they can control the reservoir levels to balance the need to prevent flooding with the need to capture water. And this figure from a paper that came out in 2019 shows the way in which the existing approach, which is based on something known as rules curves, which you might have seen in a water resources class, can be changed to use this forecast-enabled reservoir management to retain more water. And essentially what they find is that they can increase the capacity of the reservoir by about 30% without actually expanding the height of the dam, simply by using this kind of digital information. Maybe more locally and of interest to people in British Columbia and parts of Canada is the idea of using the same idea of weather forecasting coupled with sensors and actuators to operate stormwater control systems, both for preventing combined sewer overflows and for harvesting rainwater for later use. And so this is an example from a company known as OptiRTC that uses weather forecasting to determine when to remotely trigger the opening and closing of valves on cisterns and stormwater storage ponds. And by extending this idea of forecast enhanced water storage to the small scale, the effective size of the flood control infrastructure increases and makes it much easier to prevent CSOs and to manage stormwater more effectively to prevent flooding. This idea is that really, we're moving beyond the analog era when valves were either open or closed, or a team had to drive out in a truck to open up a valve, to the point where it's all controlled remotely. These initial wins with respect to the digital water system really give us a taste of what's going to come in the future, but there are still a number of barriers to overcome. And as part of the NAUI road mapping process, we identified the questions of interoperability of data from multiple sources as a key challenge that the water industry has to overcome to realize the promise of digital water. That, along with cybersecurity, which is of course coming to the fore after the pipeline ransomware attack of a couple of weeks ago, are really the issues that need to be addressed, because in the water sector, we have various types of infrastructure that all run on different types of software that are produced at different times by different vendors and have vulnerabilities when they're put on the cloud. But once these issues are addressed, I think we'll see a lot of changes in the water sector. Now, the second area which we identified where I think that we're going to see some real changes in the way that we address water challenges in the future are related to the desalination revolution. So this figure shows you the specific investment costs of desalination technologies, in this case, seawater desalination, over time for the 3 main types of desalination plants: multi-effect distillation, multi-stage flash distillation, and reverse osmosis. And for all 3 of them, the price of installed capacity has been dropping since the 1970s and is starting to level out at levels where they start to look pretty competitive with respect to the other sources of water that cities have been exploiting. So as a result, you see that in Southern California, where the largest seawater desalination plant in the Western Hemisphere came online a couple of years ago, or in Perth in Australia, or in Israel, or in Spain, seawater desalination is becoming a much more viable solution that is affordable for many city dwellers. And I think we'll see that as the world becomes wealthier and the cost of seawater desalination continues to drop, it will become more common. But the benefits of seawater desalination are restricted to the coast. The real promise for future development of desalination technologies is inland. And the problem that we've yet to fully figure out is the management of all of the salts that are produced in desalination brines. So there are tremendous resources of brackish water available inland. There may be in aquifers that are a little deeper than some of the drinking water aquifers that we routinely exploit, but many cities are eyeing these as sources of water. And likewise, when we do things like when we transition from once-through cooling to recirculating cooling in power plants, we have to deal with a desalination brine. The approach that we currently use for zero liquid discharge or for managing these brines is a pretty brute force approach. It involves using brine concentrators and brine crystallizers, which are very energy intensive. So they're not really very attractive, and they're holding back a lot of our desalination. The other challenge of this salt management, or the other possibility that would be opened up if we could figure out an inexpensive way to manage salt brines, is the salt balance in agriculture. So around the world, one of the big impediments to irrigated agriculture and things like drip irrigation is the salinization of soil. And we end up generating salty runoff when we get very efficient with our agricultural systems. And when that salt has nowhere to go in closed basins, it eventually leads to a decrease in soil fertility. Likewise, in the power sector, when we move away from once-through cooling in dry climates where water is limited, we end up with a salty brine solution after it's been used with nowhere to go. And the current approach of just putting that water in giant ponds and letting them evaporate in the sun is not really very efficient. So as we started looking at the technology horizons and what's available out there, we saw two possible directions to break through this bottleneck. One involves the use of new types of reverse osmosis systems, high pressure reverse osmosis. You can read about them in this article that came out in 2018 from the group at Yale. But you can see that basically if we can extend the range of pressures under which reverse osmosis operates by moving away from polymeric membranes to things like ceramic membranes, we may be able to recover more water and reduce the volume of brine that we have to manage. The other approach out of this bottleneck involves kind of a low-tech approach of using things like salt-tolerant plants, or in this case, actually a synthetic analog of salt-tolerant plants, something that we call a graphene oxide stalk, which uses the sun's energy and enhances the rate of evaporation of water. See, when you just allow ponds to evaporate water, a lot of the solar energy goes into heating up the water. But if you separate the water, either on a leaf of a plant or synthetic leaf of a plant, that energy goes much more effectively towards evaporation. And we found that we could get a 1 to 2 order magnitude decrease in the area needed to evaporate salts simply by using an inexpensive piece of cellulose coated with graphene oxide. And that's described in a couple of papers that we published in the last few years. But whatever way you finally manage to address the salt problem or the zero liquid discharge problem, at the end of the day, you're left with a mountain of salt without many good things to do with it. So those of you who come from maybe a chemical engineering background recognize that if you have a waste product the best thing you can do is valorize that waste product to find a way for some other industry or some other group to use it productively. And I think that's one of the big challenges of the circular economy, is that if we're going to take advantage of our enhanced ability to desalinate water, we're going to produce mountains and mountains of salt. And our choices are either to bury the salt underground or find a way to get it to the ocean, or to convert it into valuable chemicals. And what we're finding is that commodity chemicals, things like sulfuric acid and sodium hydroxide, that have multiple uses in industry, may be one path for this, but really it's a research challenge that's yet to be addressed, and something that maybe some people in this group would take on. The final theme that emerged in the road mapping process was related to the use of information technology and advances in materials and treatment to enable distributed or non-grid solutions to build small-scale treatment facilities for water. And I know that many people who focus on WASH and think about the sanitation challenge are finding that the idea of non-grid solutions makes sense when dealing with the public health aspects of managing fecal waste. But the issue of using non-grid solutions for water supply is a slightly different challenge, because water has to get there and has to be reused, and it's not just simply a matter of capturing material and returning it to the land, or getting away from the liquid water carriage system that the world relies upon. So this idea of non-grid solutions and a transition from centralized water and wastewater collection and treatment to some form of distributed system or hybrid system has been very intriguing to many people in our field, and is well articulated in this article from Hoffman et al. That appeared in ES&T in the year 2020. But the progress has been a little bit slower in terms of realizing non-grid solutions for water systems. And this could be very important for rural communities where you don't have access to a city water supply. It could be very important for places where the water delivered by a centralized water system is not safe to drink. Places where you have things like PFAS contamination, or where you have intermittent pressure making water unsafe to drink. And so we think a lot about ways in which we could either use existing inadequate centralized systems or non-existent water systems to realize this effort. And in terms of our own research, we've been thinking particularly about electrochemistry, because when you use electrodes to either generate disinfectants like chlorine and ozone, or to directly degrade contaminants, you get away from the need to replenish reagents. You develop a system that's a lot more responsive. You just have to change the current or the voltage in the system if you want to change in the operating performance. And you get something that looks a lot more manageable in terms of creating hybrids and remote autonomous systems. So we see a lot of potential there. And in fact, I wrote a paper with my colleague Cornel Rabai from Ghent University that we published in Water Research earlier this year, talking about something that we refer to as personal water systems, where you might be able to capture the rainwater on your house, to recycle that water in various ways, and to create water that's tailored to individual needs within the home, a different type of water for the washing machine and for the kitchen and for the garden, taking advantage of the advances in these modular kinds of water systems. So I gave you kind of 3 examples that came out of the NOWI road mapping process of how technological research might help enable the next path. But really, there's a larger framing of this, a social way of thinking about this, or a policy way of thinking about the next path that we need to consider. And I alluded to that earlier on in the talk, this idea of thinking about our obligation to future generations to provide water systems that are sustainable and to return more water to the environment. And I could talk about this for a very long time, but I'm kind of running out of time here. So I wanted to leave you with a thought maybe that will help this discussion. These 12 graphs here come from a paper that came out in 2015, and it's part of a larger discussion of something called the Great Acceleration, which I introduced in the beginning of the talk. This idea that in the period after the Second World War, there was a rapid increase in population and wealth and energy use and infrastructure around the world. And this article kind of broke down the Great Acceleration into different parts of the world, where the OECD countries maybe have seen the height of their acceleration and now starting to slow down, while the BRICS and the rapidly developing countries of in Africa and South America and Asia are still in this rapid growth phase. But I think that as residents of the countries that are reaching the turning point in the Great Acceleration, it's up to us to think about ways in which we transition to the Great Deceleration, this idea that we might actually be able to get by with less and have a smaller impact on the environment. And some of this is going to be enabled by the kinds of technologies I've spoken about today, the kinds of things that you're going to talk about in the conference over the next couple of days, but much of it is going to be enabled by just a change in attitude about how much resources we should be using and the ways in which we use them. And I think that that discussion or that overall paradigm is important to think about if we consider the ways in which the BRICS and the rest of the world hope to get just as wealthy as we are and live the kinds of prosperity while we all put a higher value on protecting the environment. So to leave you, I tried to talk in this brief time about the problems of the world's water, but maybe more importantly, thinking about how we might go about solving the world's water problems. I started by reviewing the concept of the hard path and those dams and reservoirs and interbasin transfer projects and aquifer exploitation that we've done really enabled the modern way of life and make it possible for billions of people to live and not starve to death in the world. And so we're stuck with those because we need those to survive. Over the past 30 years or so, we've certainly learned a lot about the soft path, and we've seen that we could get more out of the resources that we take out of the earth, and that has enabled a lot of us to continue to improve the quality of life without necessarily exploiting more of the environment. But moving forward, it's up to us to pioneer a new path, a path that I refer to as the next path, and a path that will enable the kinds of transitions that we need to get through the 21st century. And with that, I'll end my remarks and look forward to discussions with you all and the continuation of the conference. So thank you very much for your attention, and I'm looking forward to the rest of the conference.